enzyme is something like this. It's not a bigger enzyme, and you know, these three amino acids are actually not one after the other in the primary sequence of the protein, but they ended up to be very close, and they have to be really at a certain distance, because they will play a sort of attraction to the next amino acid, next one, such that then the reaction can start. So for this story, we can apply whatever we have said before about protein function. Since those three amino acids are not one after the other, but they are even more sparse, mutation that can change amino acid outside this group can really affect even the distance between these three guys, affecting the function of the enzyme itself. So, as I said, there is three types, like chymotrypsin, trypsin, elastase. We will do chymotrypsin as an example. And the other three could be very similar indeed. The transition state stabilization is a real mechanism in this process, but the enzyme itself will use acid-basis catalysis and covalent catalysis as main mechanisms. So, here is the triad, and here, not where the triad is, but a little bit on your right, there is this oxonium hole that is where the transition state will end up to make even better interactions with the enzyme. So, and you see, these are the catalytic triad, and again, they make some non-covalent contact. That is a key factor in starting the process. So anything that happened that put this guy a little bit there, or this guy there, or this other guy, that will affect the catalytic activity of this enzyme. The reaction is divided in 5 steps. And the main thing is this tetrahedral intermediate. There will be 2 of them actually. One that is really mediated the real reaction, and another one in the way back to rebuild the enzyme like originally was. So I want you to focus up here a little bit. This is the catalytic tree. Aspartate, histidine, serine, okay? This guy here, this serine, this proton is not enough acidic when it's alone. So when it's far away from this histidine. And even when, or this aspartate as well. So we'll not be able, the oxygen, to attack this carbon in a normal circumstances. So for example, in the case of mutation, it takes these 2 guys a little bit farther away. But when the protein is in normal state, what is happening is that this aspartate, the oxygen here, will polarize the imidazole ring of histidine 57, making the nitrogen in position 3 of that imidazole ring more basic. And when this guy became more basic, has a better chance, more power to attract this proton from serine 195. That is basically the beginning of everything. And that is how the catalytic period is working. So just to review this, I want to say another thing here. When this happens, then on stage 4 here, there will be a water molecule that will be, remember the water came to the rescue. That is the case, it's rescue the enzyme, and that is the way, is another tetrahedral intermediate is formed to finally leave the active enzyme, and the product can be eliminated as well. So let's focus to this one. What we said is that aspartate, this oxygen here, really can attract this hydrogen, making this nitrogen in position 3 more basic. This nitrogen then is at right distance to abstract this proton from serine 195. What happened now is that the oxygen of serine 195 is now a nucleophile, really able to attack this carbon here. And that is what happened. So we get a bond between serine 195 and the oxygen and the carbon on this side here. In the meantime, this nitrogen that is part of the peptide bond is going to look at this hydrogen. You remember, this hydrogen was originally present in serine 195. But that hydrogen now will be donated to this nitrogen here to break the peptide bond. Remember, peptide bond is 1.4 of a double bond energy, so it requires quite a bit of work to complete that. This is why perhaps there is a covalent catalysis involved. Before we go to the next step, I want to show another way to see the same identical situation, but with a different visual tool that allows us to also understanding what is happening in that stage. When the enzyme is binding, this is the enzyme. You remember, we are now used to see enzymes in this way. And in this schematic representation enzyme, there is the same identical amino acid. The catalytic triad, so aspartate, histidine, serine, but also this glycine 193, that just to make things easier to show has this funny, very elongated structure. It's not really like that, it's just that we want to see it this way. So when the reaction starts and we created here, right? The tetrahedral intermediate with a covalent bond between serine 195 and this carbon. That is the covalent bond. This one here. So this part of the protein is basically moving a little bit towards this direction, which is the area that is called the oxoanion form. When that happens, something peculiar is happening. There will be an additional hydrogen bond between aspartate 102 and the amino group that is going to be part of the peptide bond. But also two hydrogen bonds between serine 195 and glycine 193 and this oxygen. The oxygen attached to the carbon of the peptide bond. These two hydrogen bonds are spatial. The distance between the hydrogen and the oxygen in both cases is lower than the average distance of a normal hydrogen bond. So for the Coulomb law, we know that the energy of those hydrogen bonds is higher than the normal energy of a normal hydrogen bond. And if the energy is higher, that would be also more relevant to reduce the delta G of the transition state, therefore making the delta G double dagger bigger and increasing the rate of the reaction. Is this making sense? Did I told you that biochemistry looks like tango? Dancing tango, I'm not good, okay? But tango is a beautiful dance, like biochemistry is a beautiful science. When you see all that done correctly. Tango has a lot of rules. It's not like a rock and roll that you can move like you want. You have to move in a certain way, otherwise your companion feet will suffer, like you usually do. So the same is here. You have to put these concepts all together in the right order in order to explain and visualize the situation. And each of them will be part of the explanation. So you can dig in on all the stuff that we did before, or add the new things when it's necessary. So, how I can help you on visualizing this? For example, I can put together this figure that I just showed you with those figures that are on the step 2. And this is something that would be even better if you do by yourself. Just try to compare two figures that represent the same thing, but you need to figure out what is what. Helps you to learn. So this carbon here is this guy there, right? So this is the interaction that is represented there, and this interaction here is nothing else than that one, or this one. Of course, not that, this one. So when this happens, at this point, this proton can be given to the nitrogen, that breaks the bond, the peptide bond, and separates the two parts of the enzyme. This is the acyl enzyme intermediate. At this stage, this guy here can be a living group because it's done. The only thing that needs to be fixed now is the enzyme itself and this part with the carbonic group, the C-terminal. So how is fixed? Again, water came to the rescue. So from here, we eliminate this guy, we get water, and the water will be now, this nitrogen is always working as a base, will attack this proton. So this oxygen will be a nucleophile now that will be easily attacking this carbon, breaking this bond here. And that is what happened. Once this happened, this hydrogen, which originally belonged to the water, will be finding now this oxygen here. So these electrons will move to abstract this hydrogen there. So the hydrogen of the water, donated by the water, is first going to bind the nitrogen 3 of imidazole group of histidine 57, and then move it to the oxygen of serine 195. Quite a trick, but that is the order, okay? Stepwise, not just. Okay, so this is the second tetrahedral intermediate, which will easily lead to the release of an active enzyme, as was before, and the final product of the reaction. It's not difficult. What I hope I showed you by the way I represent everything, is also connecting different figures and be able to talk to those figures in order to understand the process. If you try to sit there and memorize all the steps, if you like to do that, good for you. I mean, I'm not against that. But, I will scream and cry if I get these things. So, a good visualization. If you find another book, if you have another textbook, do the same that I did. Try to take the figures of that book and compare with these figures. The reaction is the same. So, if the book is a good book, so it doesn't make mistakes, you will be able to visualize the two things and will help you to be sure to reinforce what is your knowledge. So, as I promised, there is not much more than this today. So again, review the lecture, you will have time to read the 5 pages of any textbook covering this after reviewing the lecture.